The pursuit of space, of reaching the stars, is one of humanity's most ambitious dreams. But every great leap into the unknown begins with a spark, a singular idea that drives innovation, evolution, and the desire to go beyond. The rocket engine is one such spark. It has powered humanity's journey from the earthbound to the stars, propelling us past the confines of our world into the vastness of space. From its humble beginnings to its sophisticated present, the rocket engine has undergone an extraordinary transformation. But how did we go from primitive fire-powered projectiles to the engines capable of taking us to Mars? Let's explore the evolution of the rocket engine, an invention that has shaped the future of space exploration. Long before the first spacecraft launched into the cosmos, the idea of harnessing fire to propel an object through the air was already in motion. In the 9th century, in China, the alchemy of gunpowder set the stage for the first rudimentary rockets. These were not designed to explore space, but to serve as tools of war and celebration. Chinese inventors, utilizing the power of gunpowder, created the first rocket-like devices, small bamboo tubes filled with black powder that, when lit, would propel themselves into the air. These early rockets were used as military weapons and for firework displays, a symbol of both destruction and festivity. They didn't look much like the rockets we think of today, but they set a crucial precedent. The principle of using an explosive force to push something skyward had been born. This idea, while primitive, would inspire centuries of progress. For centuries, the concept of rocketry remained largely confined to basic military uses. But as science and engineering began to advance during the Renaissance and into the 17th century, curiosity about the forces of nature, about the very fabric of motion, began to shape new possibilities. The great minds of the time, such as Sir Isaac Newton, laid down the laws that would later guide the understanding of rocket propulsion. It was Newton's laws of motion that would provide the framework for all future rocket engineers. His third law of motion, stating that for every action, there is an equal and opposite reaction, provided the scientific basis for the propulsion of rockets. It was a simple principle, but one with profound implications for the future of space exploration. And yet, it would take nearly 3 centuries for this understanding to be fully realized in a way that could break free from the Earth's grasp. In the 19th century, a new generation of thinkers, such as Konstantin Tsiolkovsky in Russia, began to imagine a future where humanity could use these principles to leave the Earth. Tsiolkovsky theorized that rockets could break free from Earth's gravitational pull, not just as weapons, but as means of travel. Though the technology didn't exist in his time, his vision would fuel the future of rocketry. The 20th century marked the beginning of modern rocketry, with practical experimentation taking center stage. In the United States, one inventor was destined to change everything: Robert Goddard. In 1926, Goddard became the first person to launch a liquid-fueled rocket into the air. Goddard's invention was a game-changer. His rocket used liquid fuel, liquid oxygen, and gasoline. That was far more efficient than the solid-fuel rockets used in earlier designs. Unlike solid fuels, which burned quickly and were difficult to control, liquid fuels could be regulated, providing more precise and sustained thrust. Goddard's rocket rose just 41 feet in its first test flight, but its success showed the world what was possible. For the first time, humanity had developed a method of controlled flight that could, with further development, reach beyond the confines of Earth. Goddard's work, however, was largely ignored during his lifetime. His true significance would only be realized decades later. as the rockets of war and exploration became increasingly sophisticated. During World War II, the power of rocket technology exploded. The development of the V-2 rocket by Nazi Germany represented a leap forward in rocketry, combining the principles of liquid-fueled propulsion with wartime urgency. The V-2, designed by Wernher von Braun, was the first long-range ballistic missile capable of carrying explosives hundreds of miles. Its launch marked the first time a rocket reached the edge of space. This was not a peaceful exploration of space, but the birth of a technology that would later be adapted for peaceful purposes. When World War II ended, the US and the Soviet Union raced to secure the V-2 technology and its engineers, leading to the Cold War-era space race. The legacy of the V-2 was profound. It didn't just ignite the future of military missiles. It spurred the creation of rockets capable of reaching the Moon, Mars, and beyond. What began as a weapon would become the gateway to the cosmos. The 1950s and 1960s marked the golden age of rocketry, the space race. The Cold War rivalry between the United States and the Soviet Union created a fierce competition to break new barriers in space exploration. The stakes were nothing less than national prestige and the future of humanity's place in the cosmos. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite, into orbit. It was a defining moment in history, one that propelled the world into the space age. This achievement spurred the United States into action, and in 1961, President John F. Kennedy set the goal of landing a man on the moon before the end of the decade. In response, NASA developed the Saturn V rocket, an engineering marvel. Standing taller than a 36-story building, the Saturn V was powered by 5 enormous F-1 engines. These engines produced a combined thrust of 7.5 million pounds, more than any other rocket before or since. On July 16, 1969, Saturn V sent Apollo 11 on its journey to the moon. The mighty F-1 engines, burning liquid oxygen and kerosene, blasted the spacecraft beyond the atmosphere and toward its historic landing on the lunar surface. This achievement was not just a triumph of rocket engineering. It was a moment that defined humanity's ability to push past the limits of Earth's gravity and gaze upon the cosmos with new eyes. As we entered the 21st century, the race to conquer space was no longer defined by Cold War rivalries, but by new goals: exploration, commercialization, and sustainability. The focus of modern rocket engineering has shifted toward efficiency and reusability. SpaceX's Falcon 9 rocket represents a monumental shift in rocketry. What sets Falcon 9 apart is its ability to return to Earth, land vertically, and be reused, reducing the cost of launching payloads into space. The idea of reusing rockets was once unthinkable, but now it's the future. By reusing hardware, the cost of space travel is significantly reduced, opening the door to private companies and future space tourists. Another game-changer in modern propulsion is the development of ion engines. These advanced systems work by using electricity to ionize propellant, creating a much more efficient form of thrust compared to traditional chemical rockets. Though ion engines produce less thrust, their efficiency makes them ideal for long-duration missions, such as traveling to Mars or even the outer planets. They could revolutionize deep space travel, making it possible to journey farther into the solar system than ever before. Looking toward the future, we stand on the precipice of yet another great leap. The next giant step for humanity in space exploration is Mars, our closest planetary neighbor, and one that we hope to colonize in the coming decades. To make this vision a reality, new propulsion systems are being developed, including nuclear thermal propulsion, which promises to dramatically cut travel time to Mars and beyond. These technologies could make deep space exploration more feasible, opening the way for humanity to become an interplanetary species. From the primitive rockets of ancient China to the reusable engines of SpaceX, from the colossal Saturn V to the ion engines that could carry us to distant planets, the evolution of the rocket engine is one of humanity's most extraordinary technological achievements. It is a testament to our endless curiosity, our drive to explore the unknown, and our desire to push the boundaries of what is possible.